Stoichiometry is the mathematics of chemical reactions. We start off with the center of chemistry, the mole. The mole is a word that simply means a set number of atoms. It's a word that represents a number just in the same way the word dozen represents 12. The number it represents is called Avogadro's number. It is 6.02 times 10 to the power of 23 of anything. But we use it in chemistry, so it's specifically either atoms or molecules. But it could be anything. The atomic mass of carbon is 12 atomic mass units per atom. We want to keep the number 12, but the reason we have the mole be the size that it is because we want to use a more convenient mass unit. So while it's 12 atomic mass units per atom, it's also 12 grams per 6.02 times 10 to the 23 atoms, or 1 mole. 1 mole is the mass of the element on the periodic table in units of grams. That makes it an extremely convenient unit to use. Take a look at this picture, and you can see that we have 4 different element samples. Each of these element samples contains 1 mole, meaning 6.02 times 10 to the 23 atoms. It's a conversion factor that looks like the fraction 6.02 times 10 to the 23 atom over 1 mole, or its reciprocal. However, the mass of each of these moles is the mass you'd find on the periodic table. So, for example, a mole of helium weighs 4 grams. You can see we're showing the molar mass 4 different ways, but they're all equivalent to one another. When we're doing calculations in chemistry, the mole is often the center part of this. So one of the most convenient calculations is conversion of grams to moles, or perhaps moles to atoms, or any combination of those. In a grams to moles conversion, we'll use a conversion factor from the periodic table, the number of grams on the periodic table per 1 mole. When we're converting moles to atoms, we'll use Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. So in the example problem, what's the mass of 3 silver atoms? Ooh, that's going to be a tiny answer. We would start with the given value of 3 atoms. We'd take it times a conversion factor where atoms cancel. That'll be Avogadro's number. And then we'll take it times a conversion factor where moles cancel. That's the molar mass. Remember to always include units with your numbers. There are no naked numbers in chemistry. Our answer, if we put it into the calculator right, is 5.38 times 10 to the minus 22 grams. Please try this with your own calculator. If you got the wrong answer, that might be because you're using the 10 to the power function on your calculator instead of the exponent function, which is either EE or EXP, depending on the brand of calculator you have. When we express the mass of compounds, we have either molecular masses or formula masses. For molecular masses, we're talking specifically about the mass of molecule compounds. For instance, water is a molecule because it's made out of 2 nonmetals. Its mass 18 is arrived at because you'd add the mass of 2 H's, 1 O, and get 18. That is 18 atomic mass units per molecule, or 18 grams per mole. For ionic compounds, we use something called the formula mass. The formula mass is not the real number of ions in the compound, because something like sodium chloride has technically an infinite number of ions, but it's the ratio. So in the picture below, you see a representation of sodium chloride. There's 1 Na for every 1 Cl, so we add 1 A and 1 Cl together. We could say 1 Na and 1 Cl ion would weigh 58.5 atomic mass units, but we'd also say the formula mass is 58.5 grams per mole. Molecular mass is not the right word because it's not a molecule. Several conversion factors are available to us. If you look at these conversion factors, you can see that molar mass is a conversion factor we could use, grams per mole. Avogadro's number works for us. Molarity, which we've not introduced yet, but we will soon, is the number of moles per liter in a chemical solution. Density, the number of grams per milliliter of a substance. The number of atoms per molecule, which I abbreviate MC, is, for instance, the number of atoms over the number of the 1 molecule. The mass fraction, which we'll discuss in a little bit, and the mole ratio, which we'll discuss in a little bit. We have these all at our disposal to use in our conversions. Let's look at this first example problem. This comes from our textbook, chapter 3.4, we can see that the question says determine the number of chlorine atoms in 125 milliliters of liquid carbon tetrachloride, and you're given a density. What can we figure out from this? Well, first of all, we could determine the molar mass of carbon tetrachloride simply by adding 1 carbon and 4 chlorine atoms together. We'd get 153.8 grams per mole. Second of all, we can tell that there are 4 chlorine atoms per 1 carbon tetrachloride molecule. That also makes a conversion factor. When I solve for this problem, just like any other conversion factor, we'll start with our given value of 125 milliliters. Let's try multiplying that by density so that milliliters can cancel out. Now let's multiply it by molar mass so that grams can cancel out. Let's multiply it by Avogadro's number so moles can cancel out. And finally, let's multiply it by the fraction that is the number of chlorine atoms per molecule so that molecules can cancel out. We're left with a number that's large, but we expect it to be large. 3.11 times 10 to the 24th chlorine atoms. When we use chemical reactions, the mole ratio is one of the most important tools we have. In the reaction between potassium and nitrogen to form potassium nitride, you can see 3 different possible mole ratios. When the reaction has been balanced, it's just a matter of making a fraction out of any 2 of the chemical compounds. So if I pose the question of how many moles of potassium nitride form when 4.38 moles of potassium react, it's a simple matter of taking the given number of moles times the appropriate mole fraction in such a way that the moles of the correct compound or element cancel. So moles of K over moles of K will then make them cancel, so you're left with the appropriate numbers of moles of K3N. In a more complex stoichiometry problem, I ask how many grams of magnesium are required to convert 83.6 grams of titanium chloride to titanium metal. You may remember this from first-year chemistry as being rather difficult, but it's going to be one of the easier things we do. Starting with the balanced chemical reaction, we imagine we can express the quantities of each compound either as a mole or some kind of measurable data. So if I create a table, we can say, hey, there's 83.6 grams of titanium chloride. To calculate to grams of magnesium, we can't do a simple 1-to-2 conversion because it's not a grams conversion, it's a mole conversion. We'll have to do 3 steps as shown by the 3 arrows. So one bit of information we have available is if we add up the molar masses, we'll see that titanium chloride has a molar mass of 189.67 grams per mole. Let's set up a similar conversion factor that we've been doing so far, starting with our given value of 83.6 grams. We will convert first to the moles of titanium chloride by dividing by the molar mass. Then we'll convert moles of titanium chloride to moles of magnesium by using a 2-to-1 mole ratio. And then finally, we'll convert from moles of magnesium into grams of magnesium by using the molar mass. Notice we don't use 2 times the molar mass of magnesium because 1 mole has the mass of 24.31 grams. Our answer of 21.43 grams of magnesium is great. We don't need to calculate anything for the other chemicals. We don't have naked numbers. We show all of our unit conversions. Finally, the last thing we're going to look at is how to use mass fractions in percent composition. A mass fraction is simply a fraction of the masses. So if I want to know the mass of an element or ion within a compound, then I simply will put part over total so that the element mass, we'll call it A, over the compound mass, we'll call it AB, is expressed using molar masses. The mass percent is nothing more than the mass fraction multiplied by 100. So for example, if I said what's the percent composition of oxygen and the grams of oxygen in a sample of glucose, we can answer both questions almost at the same time. We'll simply recognize that there's 6 oxygen atoms in glucose, which is C6H12O6. So 6 times 16 over 180 tells us that the percent of oxygen in glucose is 53.3%. Leaving that as a fraction and multiplied times the original sample size of 50 grams shows us that out of the 50 grams of glucose, 26.7 grams of oxygen would be present. So good luck studying your stoichiometry, and my boys wanted to say hi as well.
Hi! And remember to do your homework!
Those were their ideas, not mine. Good luck.